So here you are.
Great. Well, thank you very much for the introduction, Troy. And welcome, everyone, to eDay. It's great to see such a packed room. I guess many of you are Stanford alums, so welcome back to campus. Probably you noticed a lot of changes with the new engineering quadrangle. This may be the first time you've been in the Huang Auditorium. And welcome also to all of your families. The talk I'm giving today is kind of a hybrid introduction to nanoscience, geared both towards the younger audience, and there are some aspects that hopefully will appeal towards the more senior fellows as well. So as Troy mentioned, my name is Jennifer Dionne. I am a professor in the Department of Material Science and Engineering. I try not to spread that around too much because I do still enjoy getting student discounts on campus when I can. For those of you who might be movie buffs or perhaps went to the movies, I think about 5 years ago when Mission Impossible came out, you'll notice that the theme of my title slide is from Mission Impossible. And that's because today a lot of the technologies I'll be talking about were at once thought to be impossible or kind of in the realm of science fiction. And now thanks to advances in engineering and in particular nanomaterials engineering, they're becoming to the point where they are possible and are being part of our everyday culture. So I'll be talking about how we can control light-material interactions on very small scales, on nanometer scales. And then a few of the applications I'll be discussing are efficient solar cells, cancer treatments that rely on light rather than drugs, and also invisibility cloaks. So I figured I'd start off with kind of the size and scale of things. What do I mean when I say nano? Like, what is a nanometer? So for reference, let's just consider 1 meter. That's roughly 3 feet, or about the size of my hip, maybe about the height of a kindergartner, if there are any younger children here. So we've got 1 meter, and let's zoom all the way back to the outer edge of the visible universe. How far can scientists see out to the edge of the universe? If you look that far out, you'll wind up seeing specks of light. These are basically clusters of galaxies. So the size of the visible universe that we can estimate is 9.3 times 10 to the 26 meters. So that's a 9 followed by roughly 26 digits, most of them zeros. So this is 1,000,000,000, billion, trillion meters. So a very large length scale. And now let's zoom in to one of these little specks, which I said is a cluster of galaxies. And that brings us into the Virgo supercluster, which is part of the supercluster that we're in. So each of these specks of light now is an individual galaxy. And here the size scale that we're looking at is 1.5 times 10 to the 23. So this times 10 to the 23 meters means I have a 1 followed by 23 digits, 22 of which are zeros and 1 is a 5. So again, huge length scales. Zooming in here, we have our very own home galaxy, the Milky Way. That's 1.2 times 10 to the 21 meters. Zooming in yet a little bit more, we have our own solar system, which is roughly 5 trillion meters. So this is the distance from Pluto to the sun. Zooming in even more, we have our own home planet. This is a view from the Earth, from sky, looking at the Earth at night. And the Earth is roughly 10 million meters in diameter. Zooming in even more to Everest, perhaps some of you have had the chance to go to Everest. That's about 8,000 meters tall. Perhaps some of you drove past the Stanford Linear Accelerator on your way to campus. The length of the linear accelerator is 3,000 meters long. It's just up the road on Sand Hill, near where you'll get on the 280. So if you haven't had a chance to visit, I highly recommend visiting. They have a lot of really interesting subatomic particle physics that they're exploring there. Going down to even smaller scales, here we have lots of local redwood forests. The typical height of a redwood tree is about 100 meters tall, so extremely tall. The height of the typical Stanford band member is about 1.7 meters tall. So like I said, for reference, about the size of my hip is 1 meter tall. And then zooming in even more, the average size of a chicken egg is about 5 centimeters. So notice now we're going to less than a meter. Here we're at 1/100th approximately of a meter. Zooming in even further to an ant carrying a leaf, now we're at 1/1000th of a meter. So about 4 millimeters is the average size of an ant. Zooming in even more to pollen on a bee, now we're at 1/1,000,000th of a meter. This would be 50 micrometers, so 1/1,000,000th is a micrometer, is the average size of a pollen grain. If you were to look inside your blood vessels or your veins, you'd see with a microscope red blood cells. The average size of a red blood cell is about 7 micrometers. So again, about 7/1,000,000th of a meter. Going to even smaller length scales, if you were to look at different viruses, the average size of a virus is about 90 nanometers. Here, this is the HIV virus. And then even smaller than viruses, engineers can make materials down to about 1 to 2 nanometers in size. This is an electron microscope image of a single nanoparticle. The average diameter of the nanoparticle is about, well, here it's 2 nanometers, and each dot you see on the screen is an individual atom, in this case an atom of cadmium or selenium. So this is the length scale that we'll be talking about today, roughly between 1 and 100 nanometers, where we're engineering structures that can be built kind of atom by atom. And as you'll notice from this kind of power of 10 or power of 1,000 zoom through from the outer edges of the universe to the most nanoscale of objects, one of the challenges of nanoscience is that a lot of nano objects can't be seen with the visible eye. And yet so much of the universe is made up of nanomaterials. So being able to control the properties of nanomaterials and be able to tune how they interact with different things like electricity or light or mechanical pressure is extremely important to much of our daily life. All right. So in terms of nanoscience on Stanford's campus, there are a number of applications. I won't have a chance to talk about all of them, and in fact, I'll talk mostly about work that my group is doing and my collaborators are doing. But I just wanted to give you a flavor, since you might be hearing some other classes this afternoon or seeing some other demonstrations. So Stanford material scientists and engineers are looking at how nanomaterials can be engineered to make new, for example, electronic and photonic devices. So for example, organic displays, kind of organic televisions that are made of purely organic materials, kind of like a plastic that can be very flexible, also have very vivid displays. So you might imagine one day your iPhone or your iPad may be something just like a piece of paper or plastic that can be rolled up and transparent, and yet still show you the same vivid visual display that you get now on a thicker tablet. Scientists and engineers on campus here are also working on new nanomaterials for solar cells, so how you turn sunlight into electricity, for batteries, so how you can store energy in the form of chemical bonds, biomaterials for example, stem cell treatments or neuronal growth, and also catalysis for examples like water purification, how third world countries can get clean water based on new nanoparticles that allow sunlight to induce chemical reactions that allow the water to be purified. So how did I get into nanoscience? Well, the story goes all the way back to about 1987. This was me when I was about 6 years old. And I wasn't sure that nano was going to be big, but as you can see from the picture, I did have a pretty big nano at the time. So what did I want to do when I was 6? Well, I had quite the elaborate list. My first goal was to be a skating magician. I grew up on the East Coast in Rhode Island, where of course they have 4 seasons, and the winters tend to be pretty cold. But as an ice skater, I didn't mind the cold, and I wound up skating a lot, but I really also enjoyed magic. So making things invisible and kind of seem impossible. So my friends and I used to put on magic shows for our parents, and I thought it'd be great to combine the skating with the magic. Unfortunately, I could never pull off doing the axle and pulling a rabbit out of a hat. So probably around the time I was 10 or 11, I gave up that goal. My next goal was to become a Hollywood star. I always enjoyed performing, and by the time I was roughly 20, I finally got an interview from a nearby location. It wasn't quite a Hollywood studio. It was a university pretty close to Hollywood, Caltech. And for those of you who haven't seen this picture before, Caltech students are infamous for a lot of their pranks that they'll pull. So one day they went up to the Hollywood sign, blacked it all out, and then replaced it with Caltech. I didn't quite make it into the movies. The best I did was make it as an extra in Numbers. Numbers is filmed on Caltech's campus. But I did get to meet a couple of stars along the way. So I got a chance to meet with Stephen Hawking. And I don't know if any of you are Mythbusters fans, but got to talk a little bit with Jamie and Adam. All right, so upon giving up my Hollywood dream, I went back to kind of my third goal. This is when I was about 11 years old, where I really wanted to be a paranormal researcher. I enjoyed watching things like the Ghostbusters and X-Files. And you can imagine that given my trend so far, around the time I was 12, my parents started to get pretty nervous that I'd have any sort of viable career option. But in fact, I don't think being a paranormal researcher is so far removed from the sort of stuff we do now. Essentially, as a kid, I was interested in the things that couldn't be seen, and I wanted to understand the physical world and the parts of the world that seemed strange to me at the time. And a lot of my research now is interested, not so much in the paranormal, actually not at all in the paranormal, but making the unseen visible and understanding things that seem confusing based on not being able to see them with our visible eye. So my research revolves around how light interacts with materials on nanometer scales. And one of the most vivid examples, I think, of how nanomaterials can impact the visual world. First, just a quick example of the size of scale, or the scale that we're talking about when we're thinking about light. So we're thinking about nanomaterials that have dimensions on the order of 100 down to 1 nanometer. Light is basically a stream of photons, so kind of particles or waves that have sizes between 400 nanometers and 700 nanometers if we're thinking about the visible spectrum. Okay, so one of the most vivid examples of light interacting with nanostructured objects, I think, comes from butterfly wing iridescence. Here's a picture of the blue morphome. And while a lot of the browns and the blacks come from pigments, kind of like the same sorts of dyes that you would see that would color your jeans or your shirts, the blues and the very vivid like oranges and greens that you'll see in butterfly wings come from transparent, clear, kind of sugary materials that the butterfly makes. And by virtue of how these clear, kind of glass-like materials that the butterfly can synthesize, how they pack together on nanometer scales, influences the way light interacts with these materials. So let's take optical micrographs and zoom in to look at what the butterfly wing looks like on a much smaller scale. So zooming in to the region between the black and the blue, you'll notice that there are a lot of small scales that comprise the butterfly wing, kind of like your roof tilings. Zooming in a little bit more, you can get a better feeling for the scales of the butterfly wing. Zooming in a little bit more now with an electron microscope, so using electrons to image rather than light. That's why everything becomes now grayscale, because we can't see, we can't really see with our visible eye the electrons or the color. You can see now the patterning kind of towards the edge of the butterfly scale. Zooming in a little bit more, like I said, this is basically a transparent sugary material. You'll notice the periodicity in the scalings in each of the butterfly wings. And then zooming in a little bit more, where the scale bar here is about 1 micron. And remember, 1 micron is about 100 nanometers. You'll start to see, again, a deeply sub-wavelength, so kind of a smaller than the wavelength of light periodicity of the structure. So we've got both the wavelength scale periodicity, about 1 micron, and then we also have smaller scatters inside that are about 10 nanometers. So it's this periodicity of transparent materials that gives rise to the very vivid colors that you'll see in butterfly wings. Okay, so as you can see, or get a flavor for with the butterfly wing iridescence, nanomaterials can exhibit very different properties from their bulk counterparts. So here's an example of bulk silver. Silver is normally very shiny, metallic, reflective. Now, if you were to go into the lab and make tiny silver nanoparticles, so take a bulk piece of silver, and if you were to think about chopping it up in half and half and half and half until you get to the size where the chunks of silver are about 10 to 100 nanometers in diameter, and then you shine light on it, the color that you'll see will no longer be that shiny reflective silver of a big piece, say, of a mirror. Instead, the silver will appear different colors based upon its size. So here you see some blue dots. Those correspond to smaller size nanoparticles, typically with dimensions on the order of about 10 nanometers. Some of the larger orangey dots that you're seeing are bigger nanoparticles, roughly 100 nanometers in diameter. And note that here, we're just looking at an optical micrograph. So what we're seeing is basically a diffraction-limited spot. So for the adults in the audience, you're not imaging the actual size of the nanoparticle. You're just imaging the light emanating from the nanoparticle. So the size here doesn't really relate to the size of the nanoparticle. It's the color. So small nanoparticles look more blue. Larger nanoparticles look more red when they're metallic. Now let's look not so much at metallic particles, but semiconducting particles. Being in the heart of Silicon Valley, a lot of the microelectronics industry is based upon semiconductors such as silicon. Here's an example of a different semiconductor. It's cadmium and sulfur, cadmium selenide, which in its powder form is called cadmium yellow. So if there are any artists in the audience, you can go to an art store and buy a paint that's based on cadmium sulfide, and it looks this very vivid yellow color. So for example, this painting, Starry Night, or actually this isn't Starry Night, this is, anyone remember the Café de Paris? Drawing a blank right now, but a lot of the yellows in this painting come from cadmium yellow-based material. Now if we take that cadmium yellow powder and grind it up until each grain is roughly 2 to 10 nanometers across, we wind up with a cadmium selenide or cadmium sulfide nanocrystal. So cadmium sulfide nanoparticles also can look yellow when they're made in the lab, but then if you illuminate ultraviolet light beneath them, you'll wind up getting a very bright fluorescence from the nanoparticles. So for example, they can fluoresce in the green. You can also get fluorescence spanning the entire visible spectrum as you tune the size of the particle. So much like with the metallic nanoparticles, where the light that was scattered, or the color that was scattered was based on the size, here the color of fluorescence that you see also depends upon the size of the semiconducting particle. Okay, so how are these nanomaterials made? Well, one way we make them in our lab is using what's called bottom-up assembly. So we start with the atom, or basically with kind of salts and sugars that contain the precursor materials we're interested in. We dissolve them, so we basically have a bunch of different atoms in solution, and then we mix them together in the right concentrations and at the right temperatures such that they form the materials we're looking for. And my students after this talk will have some demonstrations in the lobby that you're welcome to check out. For example, here's an example of a metallic nanoparticle synthesis. So here we injected a reducing agent into a silver salt solution. And you'll notice that as time goes on, the color of the solution is changing as we're growing silver nanoparticles of different sizes. So here we have pretty small silver nanoparticles that are forming in solution. The color of the solution is now turning more orange. The particles are getting bigger, turning more red. Particles are growing bigger. So basically, we start with a single atom that seeds the growth of more atoms around that seed atom to wind up growing larger and larger nanoparticles. And now you'll see that the scattering is shifting more and more into the red. As the movie keeps playing, you'll start seeing it become more of a brownish black as the scattering kind of shifts into the infrared. So let me exit out of slide view mode. Another way of patterning nanomaterials is to use what's called top-down assembly. So you can take a big material and use ions, so basically kind of charged atoms, incident on a bulk material to pattern it. So this is a YouTube video using focused ion beam milling. So basically highly focused gallium ions here in a silicon wafer to mill lines that are each about 60 nanometers in diameter. Some of the best focused ion beam machines in the world now can pattern structures down to about 1 nanometer in diameter. And you can see that very complex patterns can be made. In this case, only the two-dimensional Da Vinci Man is being patterned, but you can also make very complex three-dimensional structures using a combination of ion beam milling or electron beam lithography. Okay, so we've learned what are some of the properties of nanomaterials, how do they impact kind of visually aspects of our world. We also learned how do we make nanomaterials. Now I want to talk a little bit about the impact of nanoscience. So here's one example from 2010 when SanDisk introduced a micro SD card that could basically store 32 gigs. When this SD card came out, it weighed about half a gram, so 0.001 pounds. It cost about $100. If you were to go onto Amazon now, you could probably buy it for about $15, and it was roughly the size of a dime. So this may sound pretty impressive because even maybe 5 years ago, I remember just buying USB sticks that were only like 512 megabytes. And being pretty impressed at the storage. Now you can go to Best Buy and buy USB sticks that are close to almost a terabyte. So I want to take you now from kind of 2010 or current day all the way back to 1980, around the time I was born, and talk about one of the Intel systems that was introduced around 1980 that had a capacity of 20 gigs. And first, this is where the audience participation comes in. I want to give you a quiz, like Troy was saying. Degrees aren't just handed out, you have to work for them. So how much do you think 20 gig storage weighed in 1980, given that in 2010, the SanDisk only weighs about 1/1000th of a pound? I made the test a little bit easier. It's multiple choice. So you get to choose if it weighed about as much as a 1 terabyte hard drive does today, so on the order of 3 pounds, or if 20 gigs weighed as much as a baby grand piano, about 600 pounds, or if it weighed as much as a Ford F-150, so about 4,500 pounds. So I'll let you discuss with your neighbor for a few minutes. All right, it sounds like there's a lot of fervent discussion, so I think we'll have some good answers. Okay, so how many people think in 1980, 20 gigs weighed as much as a 1 terabyte hard drive does today? You guys are all smart Stanford alum. What about as much as a baby grand piano? Okay, so roughly about a quarter of the audience, and I guess everyone else is for the Ford F-150? Okay, roughly half, so another quarter is undecided. Well, those of you who went last are right. So back in 1980, 20 gigs weighed as much as a Ford F-150. I guess many of you were around and using computers back in the 1980s, so maybe this one wasn't so tricky. Now, though, let's move on to the cost. So how much did 20 gigs cost in 1980? So here I made it a little trickier. Did it cost as much as a Ford F-150, or about $30,000? as much as a McLaurin F1. There's a McLaurin dealership if you go up the road into Redwood City. They've got some pretty swanky cars. So about $1 million. Or did it cost as much as Paul Allen's yacht? So about $100 million. So I'll let you discuss again, and we'll take a vote in a minute. All right. So what about the Ford F-150? Couple votes for that. The McLaurin F1? Okay, roughly maybe 3/4 in Paul Allen's yacht. All right, the rest. All right, well, you guys are super smart. So it costs as much as a McLaurin F1. If given the choice today between 20 gigs of RAM and the car, I might choose the car. So here's a picture. Back in 1980, Intel had to cascade together roughly 8 cabinets, each of which were about 3 feet by 4 feet by 6 feet. It weighed about 4,400 pounds. This unit cost roughly $1 million. And then each 2.5 gig cabinet, like I said, was about 4 feet by 3 feet by about 6 feet. So the size of the micro SD SanDisk card would be about the size of the little red button here that corresponded to the on-off switch. So computing technology has come a long way. And if you go back to 1947 when the first transistor was invented, the first transistor was pretty big in macro scale. Now you can't even see transistors. You have to go through layers and layers of your computer chips to get to the point where you can see all the embedded transistors at the bottom of your chip, and then they're wired together using metals that are kind of vertically connected above your chip. So today, the Intel quad-core i7 processor contains about 8 billion transistors, each of them with dimensions that are much, much smaller than a micron, typically on the nanoscale, with the smallest dimensions being about 2 nanometers of the gate oxide. And future research here on campus and also at Intel is working on replacing a lot of the electronics in computing with optics. So what slows down a lot of computers now is all of this metallic wiring. So the pictures on top are just the metal wiring. As you're zooming down and down into the chip, you'll also notice there's a lot of metal wiring. And the transistors are just this bottom layer. So if information could be transferred using light instead of electricity, first of all, information would be carried much faster. Nothing travels faster than the speed of light. Also, you'd have a much larger bandwidth of information. So you could not only transport information faster, but have a lot more information, since with light you have the entire electromagnetic spectrum with which to work. And then optical computers would also use much less electricity or power consumption. So your computer wouldn't heat up as much, and you wouldn't drain your battery quite as quickly. So in replacing a lot of these metallic interconnects with optical interconnects, so instead of transporting electrons or electricity, basically you're transporting photons or optical information. Intel, or actually this was IBM, excuse me, released the first CMOS integrated silicon nanophotonics chip, where a lot of the information on chip was routed using miniaturized fiber optics. And a lot of researchers on campus now are working on ways of making fiber optics even smaller. So how can you transport light on dimensions of 10 nanometers, so commensurate with the size of a typical transistor? So that would make computers much faster and able to carry much more information. So hopefully in the next few years, we might have chip-sized supercomputers based on optical computation. Another application of nanomaterials that is becoming important now, especially in the Valley and as kind of like a global issue, is in development of photovoltaic cells. So how you can turn sunlight into electricity as kind of a clean, carbon-free, renewable energy source. So probably many of you know that the sun provides more energy to the Earth than we as humans use in an entire year. But harvesting that energy efficiently is one of the main challenges of engineering today. The first solar cell that could turn sunlight into electricity was actually composed of selenium, so a semiconductor, and was made back in 1876 by William Adams and Richard Day. Kind of an ironic name, given that solar cells work during the day when the sun is shining. And basically, it was kind of, as in many of the famous discoveries of science, happenstance that he discovered this effect. He basically had taken some platinum leads and soldered them to a little piece of selenium, and then it happened to be near a candle that he was carrying around just to see what was going on. And when the candle was illuminated, he noticed that he got electricity out of his selenium chip. And he was able to attribute the effect to the light, not just to the heat. And although it wasn't very efficient, it was good enough to power basically the equivalent of a 2.5 horsepower engine. Here I'm showing a picture of the first solar-powered battery that was made at Bell Labs in 1954. And now, thanks to advances in engineering, solar cells are becoming much more efficient. So for example, typical solar cells now have record efficiencies on the order of about 28 to 29%. That may not sound so impressive for a single junction solar cell, but it's very close to what would be allowed if you consider thermodynamic considerations. So solar cells are not only becoming very efficient, but they're also becoming much easier to fabricate and much more flexible, meaning they could be a lot more easily integrated into buildings, or for example, putting solar panels not just on your roof, but having them integrated into windows. And just about a year and a half ago, there was a new solar cell that was released by researchers at Caltech that was basically a flexible solar cell that used 95% less silicon than a conventional silicon solar cell, but still could absorb much more light than a conventional solar cell and was extremely flexible. So MSNBC claimed that this new solar cell could be used to make clothing. I'm not sure you'd want to walk around with all the wiring that you need to use this solar cell, but here's a picture of it. So instead of having a bulk silicon wafer, the researchers grew basically nanowires of silicon. So you can grow the nanowires off a silicon wafer, and then you can embed them in a polymer, and then you can peel off the polymer. And for the more adult audience, typically a conventional silicon solar cell relies on kind of a planar p-n junction. This sort of structure relies on a radial p-n junction, so you can absorb light along the long axis and then extract light across the short axis. So you can get I guess, a lot of light absorption, but also very efficient charge collection. And then you'll notice here's the full solar cell. So it's embedded in a polymer. It looks kind of black or brown because it's absorbing most of the light that's incident on it. And you'll notice it's very flexible and also very efficient. So one of the problems that my group is working on is how to enable solar cells to use more of the sunlight that's accessible. So if you look at the solar spectrum, so the amount of light delivered to the Earth, basically 5% of the sun spectrum is in ultraviolet. That's what gives you a sunburn in the summer or on sunny days. About 43% of sun's light is in the visible spectrum where we can see. And then about 52% of the sun's light is in the infrared, so where we can't see those photons. So most solar cells actually are not very efficient at absorbing light that's in the infrared. So approximately 30 to 50% of the sun's energy goes to waste. So my group is working on ways of turning infrared photons into visible photons that then could be absorbed by the solar cell. So this sort of nanostructured material, which here is labeled as an up converter, basically takes infrared photons, combines them together, and then gets you back a visible photon. So here you could boost the solar cell efficiency from 30%, which is close to the record efficiency today, up to about 44%. And here's just a proof of concept where we have basically infrared or invisible light shining onto a solution of these materials that can turn the light to green. And this also can work with a very low power, non-coherent illumination such as from the sun. Okay, two more quick examples, because I know lunch is coming up soon. One example is cancer therapy with nanoparticles. I mentioned that silver nanoparticles or metallic nanoparticles basically scatter different colors of light compared to their bulk counterparts. That also means that they can also selectively absorb different colors of light. So if you make gold nanoparticles, or here gold nanocages, you can design them such that they efficiently absorb infrared light, and our tissues are transparent to infrared light. So you could shine infrared light through our tissue onto nanoparticles. They would absorb that energy. They would locally heat up, and then that heat could be used to kill neighboring cells, namely cancer cells or tumor cells that are just in the vicinity of the nanoparticle. And then you could also use the scattering, which would be at a different wavelength, to image the tumor. So you may think, oh, I don't really want to ingest gold nanocages or nanoparticles, but if those of you, some of you have been to bakeries with kind of fancier treats, you've probably eaten gold at least a couple times in your life. It's very non-toxic, so this is gold leaf. And basically gold nanocages are equally non-toxic. So you can imagine just having a cocktail of some gold nanocages, and then if you had a local tumor, you'd go into the doctor. He'd give you a little handheld laser that could irradiate your tumor, and the tumor would go away in a couple weeks, and the doctor could monitor the growth of that tumor just using scattering from the nanoparticles. And then the nanoparticles would be flushed naturally out of your kidneys a few weeks later. So this is work from Yunan Zia. He's a professor at Washington University, where he had a mouse with a localized melanoma. He injected the mouse with nanoparticles because tumors tend to be sinks for blood flow. Nanoparticles kind of naturally go to the tumor. You can also functionalize them. So here's some of the green scattering coming from the nanoparticle, so you can image the melanoma. And then you can irradiate the mouse locally just with some infrared light. And after 2 weeks of treatment, the T's indicate the tumors, you'll notice, and the red indicates the size of the tumor. So the A and B are, I guess, views from the top. B is 2 weeks after treatment started. And then the bottom images are kind of cross-sections in the vertical direction. And after 2 weeks, the tumor had largely disappeared. So sorry for the graphic image here, but this treatment is now being used to treat breast cancer. It's in FDA trials, and from the researchers working on this technology, it should be approved within the next year or two. So just injecting yourself locally with gold nanoparticles. The nanoparticles go to the tumor. You get irradiated with infrared light. The heat kills the cancer cells, and then the particles are flushed out of your system. So kind of a photothermal cancer treatment. The last two examples for what nanomaterials can do in terms of being right on the verge of science fiction would be to make a cloak of invisibility, much like Harry Potter. So different nanomaterials can allow light to be steered in very unique directions. So here's a simulation of light coming in from your left-hand side. The light is basically represented by waves of blue and red corresponding to the amplitude of the light, so high and low. And then it goes around here, just a cylindrical shaped cloak composed of different nanomaterials. That cloak guides light around the central green region, so you could put any object in that green region, and you'll notice that light never penetrates that green region. Instead, it emerges on the other side of the object or the cloak just as if it's a plane wave. So light comes in, light goes out, the light looks identical. It's never interacted with the object in between, meaning there's no scattering, there's no shadow that's been cast. So this is one way of making an object invisible to a viewer who would be on the right-hand side, because it looks like light has just passed through empty space. Another, I think, more compelling technology that could be realized that's kind of in the same category of cloaks of invisibility are perfect microscope lenses, optical microscope lenses that could allow you to image things like proteins or DNA just using light alone. So I mentioned that a lot of these nanomaterials are invisible. to the naked eye. Usually we need to use electron microscopes because electrons are much, much smaller than photons, so you can image much more fine features. But if you could just use light to get the same sort of resolution as an electron microscope or as an atomic force microscope, here's an AFM or atomic force micrograph image of pentacene, which is just 1.4 nanometers long. You can almost see the individual carbon atoms in the pentacene. That would be really a breakthrough technology. And these two technologies, while they may seem unrelated, actually rely on the ability to tune the refractive index of materials. So basically, can we create new nanostructured materials or new kind of, I guess, molecules that give rise to unique refractive indices? So here are just a couple simulations. So water composed of 2 hydrogens and an oxygen. And if you were to look at a glass of water with a straw in it, you'd see slight refraction of the straw based on the differences in the index of refraction between air, which is 1, and water, which is a little bit higher, 1.3. Now, if you, like I mentioned, these cloaks and perfect lenses rely on the ability to tune the index all the way from, say, positive values, which is what you find in nature, down to near 0 and even negative values. So let's look at a simulation of a negative index material. Here the straw gets refracted the other way, and you'll notice you can't see the bottom of the glass. So some pretty unusual optical properties with negative refractive index materials that, like I mentioned, would give rise to the opportunity to make these diffraction or microscope lenses that could allow you to image proteins or DNA, or to make invisibility cloaks. Here are a couple larger scale simulations: a pool with normal water, a pool with water with hypothetical 0 refractive index, kind of looks like a mirror, and then a pool filled up with negative index water. And these lines correspond to the edges of the pool, right? So basically the walls of the pool look like they'd be shifted out based on the way light would be refracted from air into this negative index water. Okay, so I have about 1 more minute, and I just wanted to sum up with some engineering challenges for, I think, the younger generation. I think one of the big challenges that is faced by your generation would be making highly efficient, cost-effective solar cells, so ways of coming up with carbon neutral or carbon-free sources of energy. Improved battery technology, so ways of storing energy more efficiently. Environmental materials engineering, so things like water purification. Advanced computing, optical computing, or quantum computing, spin computing. Improved display technologies, like going from 2 dimensions, say, to 3 dimensions, or improved imaging technologies in the biomedical realm, and also improved therapeutics. So a few pieces of advice on how to be a successful engineer, since many of you are probably budding scientists. I guess tip number 1 would be to stay curious. Don't be afraid to ask questions. Always be, on the lookout for new discoveries, and kind of keep an open mind. Stay in detective mode, and I guess always try to look at things from different perspectives. Perhaps some of you have seen this street art by Julian Weaver. It looks very much like 3-dimensional art from one angle, and if you look at it from a different angle, it's just kind of a stretched out painting, so or chalk art. So stay curious and stay interested. Probably the first piece of advice I can give you. Second piece of advice is to, as a budding engineer, try to always have a spirit of service. I think one thing that distinguishes engineers from kind of more fundamental scientists is that we feel compelled to serve society, whether that's working on technologies that could allow, say, mind-controlled prosthetics, or developing new renewable energy technologies, or even developing new technologies to, let Tour de France winners come in even faster, like new bike frames, say, as material scientists. But, always have that spirit of service. And even if you don't go into engineering, I think these are the 2 good pieces of advice just to keep in terms of being a productive member of society. And then lastly, have fun. So whether you're making a motorized couch or going to Stanford football games or participating in the band, just enjoy what you do. And I guess I'll conclude with a